Hi, my name is Pratik Safaraju, and this is my final project video for remote sensing. For this project, my goal was to design, integrate, and test my very own field-deployable LiDAR sensor using Raspberry Pi and OpenCV. Using this sensor, I identified a target of interest in our very own UMD campus and collected 3D measurements of the target to create a 3D point cloud as well as a 3D mesh. Ultimately, the work in this project not only allowed me to learn about remote sensing techniques, but also helped contribute to creating a 3D map of the UMD campus. My target of interest is an outdoor grill located behind the South Campus Commons 2 apartment building. I chose this target because of its interesting structure, ease of access, and it seemed like a challenge I'd like to tackle. Some key features include its fully black color, detailed features, and an odd shape that could reflect light in an unexpected manner. Before we can begin scanning our target of interest, we must first understand remote sensing. Remote sensing is the science, technology of obtaining information about a target without having a sensor in direct physical contact. Remote sensing can be split up into passive and active sensing, where passive has no self-generated radiation while active does. In fact, this is where LiDAR comes into play, as it uses laser light as radiation. In light detection and ranging, also known as LiDAR, laser light serves as the radiation source and shines on our target of interest. It is then backscattered uniquely based on the object and detected and revived by analyzers. The principles of remote sensing applied to our project because we'll be using LiDAR to obtain XYZ points of our target of interest. With these principles in mind, we can talk about the design of our LiDAR sensor for this class. The line laser serves as a transmitter and shines a red line on our target of interest. The Raspberry Pi camera serves as our receiver and records an image of the laser on our target of interest. Then via computer vision and the use of our Raspberry Pi and OpenCV, we can analyze our images to get the XYZ points we desire. Everything is held in place through the use of the 3D printed LiDAR mount, zip ties, and tape, and is then attached to an ordinary camera tripod. My laptop is used to interface with the Raspberry Pi as needed. Next step is sensor calibration. In this step, we did both single beam configuration as well as line laser configuration. Ultimately, the process involved using our sensor to range to an object or wall at known distances. The distances were calculated by the sensor were then graphed with these known distances and are displayed on the graphs here. Along the way, the radian offset and radians per pixel pitch needed to be changed to result in a better fit. For the line laser, these values were found to be negative 0.00008 and 0.00009 respectively. Here we can see that for the line laser, our sensor is most accurate past 5 feet. The collection procedure. We go and shine our line laser on our target of interest while recording the angle, and use our Raspberry Pi to record an image. We continue this process until we have scanned an entire side of our object and repeat the procedure for the remaining sides. In practice, it looks like this. Hey, so I'm out here doing my data collection, and as you can see, we have our LiDAR sensor already set up over here, bubble over there that I used to do all the angles, and we have our laser shining on my target of interest, which is a grill behind my apartment. So during the actual data collection phase, we're going to be running the Pi data collection. So all it is we run that there, and it's going to ask us to prompt the angle. So right now it was set to about 5 degrees, and so when we type our angle in here, we quickly we hit enter and tells us to confirm the angle, and eventually it's going to take a picture and store it in a folder that I specified. But while that's running, we can kind of talk about my folder structure. So over here, we have all the different folders I made. And so we have images back, front, left, right. So all the 4 sides of the grill that I think are required to make the 3D point cloud complete. And so the one we just took there was going to go in images front. And we can see it took the 5 degrees out of here. And so in the interest of time, I already did all my data collection. And so we have all the pictures I took off the front side here, and we'd have the same thing in all the other folders. Challenges I encountered included the black color of the grill, which oftentimes made the line laser near impossible to see. This was solved by using a longer exposure time. Numerous light sources like lamps and apartment lights also created lots of noise in the images. These issues were addressed by MATLAB filtering. So the first step to do is actually to go ahead to our color picker, and this is an example one that we're going to be using here, which was the one I took at 8 degrees for the back. And so we're going to go ahead and run the color picker. And the goal of running the color picker is we want to identify the HSV values so we can properly isolate the laser. So we're going to pick some stuff until it looks like it kind of covers the range we want, and we can kind of see the laser pretty well. So it looks like 120, 70, and 60 will do the job for us. And then our next step would be to go to the data generation part of the code. And so important thing here is we've already put all of our JPEGs for the images back in a folder. That's the folder we're going to be going through. And we want to also make sure some important things are, again, here we put our HSV values over here, and I already did that for us there. And then the next step would be to make sure our RO and RPC values match what we did from our previous homework to make sure that we have really accurate distance measurements. And then the next step would be to go ahead and run the code, and it'll go through all the different images and create a text file. Next, we go into MATLAB and open all the text files that we just created using our data generation code. So once we have the XYZ points for the 4 different sides of the grill, we can begin to plot them. So once plotted, we see that there are parts that resemble the grill, but it's plagued by a ton of noise from outside sources of light, such as the lamps we talked about, as well as the apartment lights. So this is just no good. So the next step is to then filter out some of these outliers. So we go ahead and filter out some of these outliers by using AND statements and looking at where we see the noise and what we know to be noise, and we can go ahead and eliminate some of those points entirely. So once we go ahead and filter out for these noise, we see that our new point clouds are much better, and we can clearly see this is the front side, and we can see the right, the left, and the back. And so once we have something that we're happy with, we can go ahead and convert these into point cloud objects. The advantage of converting to point cloud objects is this allows us to apply translations as well as rotation matrices to begin to manipulate our point clouds to create one cohesive 3D point cloud. So for example, here for the right side, we want to translate the X by 78, the Y by -62, and the Z by +5. And after all that, we want to go ahead and rotate it 90 degrees. So once we do a similar style transformations for all the different sides, we can then plot them all together, and we result in the cohesive 3D point cloud we see here, which honestly resembles the grill very well. Here we have a side-by-side comparison to the real grill as well as our created 3D point cloud. And although some detailed features such as the tray is missing in our 3D point cloud, much of it is very much encapsulated in the 3D point cloud that we managed to create using our LiDAR sensor. Before creating our mesh, it was actually important to downsample the point cloud, as we just had simply too many points for the mesh to handle. So once we go ahead and downsampled it and created a new text file called XYZ mesh, which is what we will be used to be creating the mesh. But here you can see the comparison on just the ordinary point cloud that we created and the downsampled point cloud. In fact, it's almost a little much harder to see the grill because it is just points. This allows us to have a much better point cloud to work with when we're creating the mesh. Next, we open up MeshLab to begin creating our 3D mesh. So let's go ahead and import the mesh with the XYZ points we just created in MATLAB. And we have to make sure our separator is actually space, and we go ahead and upload the point cloud. So let's bump up the point size so we can begin seeing what we're working with. So we still see that there's some noise left over, so we can go ahead and remove that in MeshLab actually. Now once we're done removing all the noise, we can begin creating the 3D mesh. So let's go over here to render. We want to show normal. And so once we go to filters, normal, curvatures, and orientations, then we want to compute normals for point sets. And the number we're going to be messing with here is the neighbor number. And so if we apply 10 here, we see it's not amazing because everything's kind of pointed in random directions. We want all the normals to be pointed outward and in the same direction. So after a lot of playing around, I saw that 50 worked really well for me. And so with that in mind, we can go and actually create our mesh. So we go to remeshing, simplification, and reconstruction, and then to screen Poisson surface reconstruction. So let's go ahead and create the mesh. And we see here that although it's not amazing, it does actually resemble the grill pretty well. So we see the body here, and then the actual stand down here. And so there you have it. That's our 3D mesh after converting our 3D point cloud to a 3D mesh. In conclusion, we successfully created a field deployable LiDAR sensor and mapped our target of interest to produce a relatively successful 3D point cloud and 3D mesh. Although there were challenges along the way, ultimately I persevered to produce results that I am genuinely happy with.